All right, this video is going to be about buffers. We're going to start by talking about the common ion effect. We saw this a little bit in Le Chatelier's principle, how when you add or remove a component that's present in a reaction, um, that it will cause a shift to occur. There should be a double arrow for that particular equation. I can't remember if it was I couldn't edit it or not. Sorry about that. But we saw this in our lab with NaCl, how we were able to dissolve a lot of NaCl in our test tube, and we filtered it out, and then we added a source of chloride ions to the test tube, and it caused the salt to precipitate back out. If you're dealing with acid-base reactions, that can shift the pH of your mixture, which is how buffers can come into play. And the reaction below is showing how when you add sodium chloride, it would shift it towards the reactants. More silver chloride precipitate would form. If you took chloride out of the mixture, let's say you added something to it that would precipitate it out, like lead, you would actually cause more of the silver chloride to dissolve. Or if you added something that would remove the hydroxide, or added a source of silver ions, those two would cause shifts in your equilibrium. Um, Buffers are going to consist of either a weak acid and a conjugate base or a weak base and a conjugate acid. I'll talk about that more in a second. But when you just have one of them separate, and I believe we saw this in our last, no, we didn't get to do the buffer lab, I'm sorry. We did see this a little bit with our Ka lab. We had the weak acid, we dissolved it and split it in half, and then we added the base to it until we caused the color to change. So the pHs differed depending on whether we were dealing with just the weak acid or just the conjugate base. And then we mixed them together and measured their pH when they were combined. And when we had them together in the mixture, we actually did have what was called a buffer. And the reason we will see that the pH is not the same is that you have the ion present that would be formed if either the weak acid or conjugate base was present alone in water to begin with. Okay, so buffers are really important in the human body. They also play a role with saline solution if you wear contacts. They basically help to resist the pH changes that take place when strong acid or strong base are added to a mixture. If you have a heart attack, one of the first things they want to do is get your heart going again because they don't want the pH in your blood to change drastically. When that starts happening, that can mess up a whole lot of enzymes and things like that, cause them to degrade, not work properly, and that can cause issues on a cellular level that your body might not be able to recover from. So to have a buffer, you have to have two components. You have to have, again, the weak acid or its conjugate base, and you have to have the weak base, or you have to have the weak base and its conjugate acid. The reason that they need to be weak as opposed to strong is what we're going to see is that strong acids and strong bases completely react, while weak acids, weak bases only partially dissociate. So they're not going to change as rapidly as a strong acid or strong base would. Um, and so we definitely want to make sure that we have components that are going to be able to resist changes in the addition of strong acid or strong base. And we also want to make sure that they don't react with one another. You can't have a strong acid present. You can't have a strong base present along with their conjugates. Um, if you have a strong acid and it's paired with a weak base, all they're going to do is neutralize one another. They're not going to be able to handle subtle changes in pH. What we will see when we get further along into this is that when you have something strong present, it's going to get consumed as much as possible before we can examine what the pH is. Whereas when we have something that is weak present, we can use equilibrium to determine its pH. So on your note sheet, I've got these two examples written down for you. Um, Normally, what I do is work these through in class, but what we have is HF and NaF. If you look at your chart for Kas and Kbs, you're going to see that HF is a weak acid. It's not one of your six strong acids. Um, Reaching down to grab my chart, sorry. HF has a Ka of 7.2 times 10 to the negative fourth. And because it's an acid, it's going to react with strong base when it's added to a buffer. And it's going to produce water and fluorine ions. So there you see that common ion, the conjugate base of HF. Sodium fluoride is a source of fluorine ions, and the fluorine is the conjugate base of HF. So it's going to react with any acid that's added to your equilibrium mixture, whether it be in the form of H plus or H3O plus, and it's going to make the conjugate acid. So you can see how in both of these particular examples, the weak acid HF produces sources of F minus ions, while F minus will be able to produce a source of hydrogen fluoride. So they both complement each other in that they may lose some of what they had initially present by moles, but they produce their counterpart when reacting with that strong acid or strong base. Same thing happens with ammonia and ammonium chloride. Ammonia is a weak base. It's got a pH of 1.8. Sorry, let me make sure I've got this right. Usually this is the one I know. Wow. Yeah, 1.8 times 10 to the negative fifth. And ammonium would be its conjugate acid. The chlorine is just part of the salt that gives us that ammonium ion, just like sodium was a part of the salt that gave us sodium fluoride. Ammonia, being a weak base, reacts with acid to produce ammonium. Ammonium, being a weak acid, reacts with the strong base when that's added to your buffer mixture to produce ammonia. So, in both of these examples, um, the acid component of your buffer reacts with any strong base that's added to the mixture. The basic component reacts with any strong acid that's added to the mixture. And then they both end up making their counter conjugate, which can then be used to determine what the pH is after the strong acid or strong base has been added. Okay, so I said before that whenever you want to know the pH of a buffered mixture, you can find the pH of it just using your equilibrium expression. But if strong acid or strong base is added, you've got to neutralize that addition. Strong acid, strong base does not want to sit around. It's not going to be present partially. The hydrogen ions, if they are added from a strong acid, would react with any base that's present in the mixture. The hydroxide would react as complete as it can with any weak acid that's present in the mixture. And there's a couple ways that you can determine what the pH is. We can use our Ka or Kb expressions to figure out the hydrogen or hydroxide that's present and then use that to find pH. Or I'm going to show you an equation that basically takes some of the math out of it and allows you to use the amounts of your weak acid and base present after the neutralization process has occurred to calculate pH. And that's called the Henderson-Hasselbalch equation. So this is an equation you would have been given in class if we were there, that the pH is equal to the pKa plus the log of the conjugate base over the weak acid. POH looks a lot like pH. It would be equal to the pKb plus the log of the conjugate acid over the base. If you take a Ka expression and you solve for pH from the hydrogen, that's how you get this equation. I'm not going to go through the derivation for you right now. If you want me to show it to you, let me know and I'll put it up on Classroom. So I'm going to show you two ways to do part A. And after this, I'm just going to show you Henderson-Hasselbalch, but I did want to give you an example of how this works with your regular Ka expression so you can kind of relate it to what we've done previously. In this particular one, we're just making our buffer. we have 1 mole of ammonium chloride that's being added to a liter of 0.7 molar ammonia. There's no strong acid, there's no strong base present. Ammonia is a weak base. Ammonium with one extra proton is its conjugate acid. So if I take the ammonia or if I take the ammonium and I drop it in water, it's going to produce ammonia and hydrogen ions. And hydrogen ions are a source of pH. Or hydrogen ions can be used to determine pH. So if we're going to use our Ka expression to find the hydrogen ion source, we need to know our Ka value, which will be on your chart, that table 17.3, and that's 5.6 times 10 to the negative 10th. And our Ka expression would look something like this with the two products over the ammonium ions. We do need to have concentrations in our brackets. So we have 1 mole of ammonium chloride. That would be 1 mole of ammonium ions. This is 1-to-1 ratio. And we have a liter of solution. So our concentration of ammonium is 1. Our concentration of ammonia is 0.75. And our Ka value is the 5.6 times 10 to the negative 10th. So I substitute in what I know, and I math it out to find hydrogen's concentration, which I got to be 7.5 times 10 to the negative 10th. I then can take the negative log of that value to get the pH. There were 2 sig figs in the concentration, so I need 2 decimal places in my pH, 9.12. If I'm doing Henderson-Hasselbalch, it's going to work pretty much exactly the same, but I would need to take the negative log of my Ka to get my pKa. Your Ka still is the 5.6 times 10 to the negative 10th. Why you're not moving? All right. Sorry, there was something on the screen I was trying to get rid of. The negative log of that would be 9.25. And then I plug in the concentrations I have of my conjugate base, which would be, in this case, the ammonia. It really doesn't matter which one you pick, pH or the pOH for Henderson-Hasselbalch, as long as you know which component in your mixture is the acid and which component in the mixture is your base. Remember, the acid should always have one more proton than the base. So I put the base concentration 0.75 on top, and I put the 1 molar concentration of ammonium ions, my acid, in the denominator. And when I math it through, because of decimal places, this one ends up being a whopping 0.01 different, 9.13. I don't care which way you choose to go about solving for pH. I'm going to use the Henderson-Hasselbalch from here on out, but either one will work as long as you are using your concentrations correctly for the base and the acid. The other two examples we're going to take a look at are going to involve the addition of a strong base or a strong acid. In this particular one, we're using strong base. And remember, we said that base reacts with acid, so it's going to react with the ammonium part, the NH4 plus part of my buffer mixture. So when ammonium reacts with the hydroxide, it produces ammonia. I should have water in there. Sorry, I left that out. Remember that initially we had 0.1 moles of the sodium hydroxide. We had 1 mole of the ammonium ions. Again, this is going back to part A. And because we had 1 liter of 0.75 molar ammonia, we had 0.75 moles of ammonia, present before we added this hydroxide to it. We have to stoichiometrically use up as much of that strong base as we can. And they're all in a 1-to-1 ratio. So if we look at our changes in terms of X, if we have to consume all of the strong base whenever possible, we're going to take away 0.1 moles from both the ammonium and the hydroxide ions, getting the hydroxide down to 0. But because those are consumed, the ammonia will have increased by 0.1. That causes ammonium to go down to 0.9, and that causes the ammonia to increase from from 0.75 to 0.85. Notice that the 0.10 had 2 decimal places, 0.750 had 3 decimal places, so I wanted 2 decimal places in my answer. At this point, I still have a buffer because I still have weak base and I still have conjugate acid, or I still have weak acid and conjugate base. They're going to be in the solution together. They're still going to have a volume of 1 liter. So if I look at my Henderson-Hasselbalch equation, the pKa is going to be what it was before. It's still going to be the 9.25 using the Ka of ammonium. But I don't have to change these back into concentration because they would both be divided by the same amount. They're a ratio. So that's one of the nice things about Henderson-Hasselbalch is that if you are dealing with moles or molarity, they can both be substituted into that ratio in the same manner. So I would take my 9.25, my pKa of the ammonium ions, and I would add to it the log of my base, the ammonia, the 0.85, divided by the conjugate acid, the 0.90 ammonium. When I do my math, I'm going to get that the pH changed by 0.025, and that caused the pH to actually go up from our previous example. We were at 9.12 or 9.13, depending on which one you were looking at. This time the pH went up slightly to 9.23. Now, if we think about it, this kind of makes sense because the base consumes some of my acid and it produced weak base, but it still did produce base. So if we lost some of our acid, the concentration in the denominator went down by 0.1 and the concentration of the base increased by 0.1, we would expect the pH to increase. And with a buffer, it does, but it only did slightly because you still had components of that weak acid and conjugate base present. In this example, we're going to look at HCl. HCl is a source of strong acid, so it's going to react with the basic component of our buffer, the ammonia, and it's going to produce ammonium ions. Again, the initial amounts that we had of ammonia and ammonium aren't going to change. We still had 0.75 moles of ammonia, and we still had 1 mole of ammonium ions. But now we have 0.1 moles of HCl that are present. Strong acid's present. We need to consume it. That's why you see the single arrow. We always have to consume any strong acid that's present or strong base whenever possible. So the hydrogen and the ammonia will decrease by 0.1. The ammonium will increase by 0.1. And so when all is said and done, all of the hydrogen ions, our limiting reactant, will be gone. The ammonia will have decreased by 0.1, and the ammonium ions will have increased by 0.1. So we've used up some of our base this time. We've increased some of our acid. So my guess is you should be able to predict from that initial pH of the 9.12 or 9.13 whether the pH should go down or whether the pH should go up based on the addition of the strong acid. We'll be able to mathematically determine what change took place or to verify which change took place using our Henderson-Hasselbalch equation. Again, the pK is still going to be 9.25, the base is still the NH3, and the ammonium is still the conjugate acid, the 1.1. And again, you could use the same information with your Ka expression if you so choose to find your hydrogen. Trying to think. Yeah, you should be able to just to do it straight with the Ka expression as well if you would like. My hope is that some of you predicted that the pH would decrease because we had an increase in acid. And since we have more hydrogen ions present, we should have a lower pH. And we used up some of our base. And it did decrease, going in the opposite direction from that initial one down to 9.02. So this is just to kind of give you an idea of why buffers would be so important in the human body and in other practical applications because they're able to resist pH changes, which can lead to a cascade of other effects that might be more substantial. So how effective a buffer is will depend on its capacity, how much it can handle additions of protons or removal of protons without causing the pH to change a whole lot. You would not want to have a buffer made with acetic acid if you wanted your buffer to have a pH of 8, because acetic acid is going to cause that pH to be much, much lower. You also need to have large amounts of the weak acid and conjugate base present. If you're down to a very little amount of one of the two components, your buffer might work well in one direction, but it won't work well in both. And you want to make sure it can resist changes in both directions. So these are three different examples of buffers involving phosphate. We've got H3PO4, NaH2PO4, NaH2PO4, and Na2HPO4, Na2HPO4, and Na3PO4. Now, the sodium ions again are just present because these are coming from salts. So we're going to be focusing on the fact that H2PO4 minus is the conjugate base of H3PO4, that HPO4 minus 2 is the conjugate base of H2PO4 minus, and that PO4 minus 3 is the conjugate base of HPO4 minus 2. How we can determine which one of these would work most effectively if we want to have a pH of around 7, again, is going to depend on how these two work in concert with one another and how much of a change we're going to have to make with the amounts of these two components to get the buffer to exist around a pH of 7. And we can look at this by looking at their Ka values. All three of these acids, H3PO4, H2PO4 minus, and HPO4 minus 2, are on your chart for Ka values. We see that the Ka of H3PO4 is 7.5 times 10 to the negative 3. So if I was going to take the negative log of that one, I would get that its pKa is 2.12. That's pretty acidic. If we had equal amounts of weak acid and conjugate base, our pH would be around 2 if we look at Henderson-Hasselbalch. That'd be really hard to get up to 7. If we look at the second example, we see the Ka is 6.2 times 10 to the negative 8th. The pH of this one is 7.21. We would need a little more acid in this buffer to get the pH to 7, but we would still have roughly I'm not going to say equal amounts, but we would definitely have amounts that are more closer to a 50-50 split with this one than we would in the first example. In our last example, we have a Ka of 3.6 times 10 to the negative 13th, which would give us a pKa of 12. That is really, really basic. You would need to have a whole lot of PO4 minus 3. I don't even know if you can make a buffer exist with these two and get that pH to 7 with these two components. Actually, you want more PO4. I'm sorry, you would want more HPO4 minus 2. So the one that would be the most effective with a pH of around 7 is going to be the one whose pKa is closer to 7, so that you can have you can be more close to a 50-50 split between the two components. And so in this particular example, it would be B. Okay, so that's the end of buffers, and we will be moving on to titrations next.